organizers, I should thank our super organizer, who was Juan, for not only convincing Nati to do this, but really making it too easy for the rest of the organizers. And well, I also I've known Nati, I guess, for more than half of my life. And I'd like to apologize to Greg for this mistake here, because in fact, the first project that I worked on as a graduate student was heavily based on Nati's paper with Greg, and so I should have caught this pentagon versus hexagon issue. Okay, I'd also like to thank my spectacular collaborators, Clay Cordova and Thomas Dimitrescu. And I should say right now that when I say things like this, I'm not exaggerating or just being nice or something. They really are spectacular. And so I'd like to thank them for the wonderful collaboration. Okay, so time out for a little bit of nostalgia. So it was 25 years ago today that I was in my last year of graduate school, and I was getting ready to apply for postdoc jobs, and by far my first top choice was Rutgers. And they had recently had this new group of 6 rock stars. Some of the 6 are Dan, Steve, Mike, Tom, Nati, and I guess that's 5. The 6th is Sasha Zemlachikov. And I really wanted to go there, and I especially wanted to work with Nati. I had already met Nati on a few occasions in grad school, and I knew him from his papers and from these meetings, and I'm indeed very, very fortunate that it worked out for me. Again, this is an understatement. Which is Tom? This one. Oh, you're right. This is Tom. On the small thing, it was hard to tell. Yes, thank you for catching the typo. By the way, I'd also like to invite Clay and Thomas when Nati asked the penetrating questions at the end to help me out. Okay, so after Robert's talk, I thought about the verb to cyborg, and I realized that this was something that I tried to learn from Nati's mentorship over the years. And so this was just something that I very quickly wrote down. I don't know if it's very accurate, but to cyborg, I guess, is to identify an interesting question or issue. This is all much easier said than done, of course. Identify the symmetries, distinguish between the global and the gauge symmetries, the discrete symmetries, the broken ones, etc., and make a table. Then notice that many things that might have been discussed before are completely vague, and they need to be made precise. And by doing this, you uncover some previously unappreciated puzzles and or subtleties. And as Nati's, as a collaborator, this is often the most fun part of the collaboration, because there's a concrete puzzle, and then it's like a challenge to try to solve the puzzle. And so this is great. And eventually, thanks to Nati, they're solved by some new ideas and methods, and then move on to the next topic and repeat. Okay, so to quote a question from Nati's webpage, we can ask, what is quantum field theory? And in a way, maybe it's like these nearsighted people who are trying to understand what this elephant is. When we first meet quantum field theory, we meet it in textbooks as perturbation theory around free field Lagrangian theories. And over the years, we've come to learn that there's so much more beyond that. For instance, there are 5D and 6D superconformal field theories, which from the Lagrangian point of view should never exist, because anything that you write down with free fields and interactions, all the interactions are in fact irrelevant. That's irrelevant. Okay. But anyway, once you have these 5D and 6D superconformal field theories, you can then try to renormalization group flow down and see where you end up. And so we can study these conformal field theories and their perturbations, and maybe some of this will lead to something that's crucial for the future. Now, just to come back to the F in this superconformal field theories, this is taken for granted now, but it was originally a shocking and controversial claim. And I remember very distinctly when Nati first told me this. At the time, there was a lot of discussion of tensionless string theories. And so the picture was you take 2 M5 brains, you connect them with an M2 brain. From the point of view of the world volume of the M5 brain, there's a string, and then when the M5s come together, the string becomes tensionless. And so there's this bizarre, mysterious tensionless string theory. And Actually, basically 20 years ago today, thanks to Nati, Nati made the shocking claim that, in fact, these are just quantum field theories. And so there were these two papers. This one was originally came out from August. This one, is basically 20 years old, just before Nati's, I guess, 40th birthday. And so quoting from his 60 paper, I decided to quote this whole thing because I think it's a great quote and it's still true today. So these theories are often referred to as tensionless string theories. Is our view that they're conventional interacting local quantum field theories. This possible interpretation was first mentioned in Edward's Proceedings from Strings 95 and Nati's paper with Edward on string dynamics in 6 dimensions. And it became more clear that after one of these theories in 3 dimensions was given a Lagrangian description, this was our 3D paper, where the Lagrangian was the mirror dual theory. And the renormalization group flows out of the 5-dimensional theories appeared consistent with the field theory. This was the other paper from just a month earlier. And it's likely that some of these theories do not arise under renormalization group flow from a free field theory at short distance. Therefore, they do not have continuum Lagrangian descriptions. It's an extremely interesting and challenging problem to find a good presentation of these theories, which is, I think, still true today. And just to mention, very shortly after that, Nati wrote a paper on new theories in 6 dimensions. Unfortunately, he called these theories new theories, which calling something new is like calling something a new supersymmetric index or something like that. It's a name that doesn't really stick. And for some reason, somehow the new got changed to L for little or something. But this wasn't Nati's doing. Anyway, so these are some, this is hard to see, but it says these are not local quantum field theories. So these are the little string theories. And often these two notions of which is the quantum field theory and which is not the quantum field theory often got mixed up thereafter. But, well, certainly not in Nati's work. And there was some brief controversy about leaking from the brain into the bulk, and then it kind of became more clear what was happening after Juan's paper on ADS-CFT. Okay, so back to the talk. If we think about renormalization group flows, so we have these pictures of renormalization group flows, like flows of water down in some monotonic way, which is like decreasing the number of degrees of freedom. And as a kid, I liked this game of chutes and ladders, so I think about this game of chutes and ladders. So the relevant operators are like these chutes which take you down, like the Higgs mass, and the irrelevant operators are like these ladders, like the dimension 6 BSM operators that we could try to use to climb up. And we often have to guess where it goes and check using the A theorem and symmetry and anomaly matching indices. And there's an interconnected web of Seiberg dualities, many generalizations, interconnections, and checks. Okay, so if we try to study this elephant, we might, in order to well, let's say to Seiberg it, the elephant, what we could do is we could try to start off with some case with many symmetries. And so, for instance, we could start with superconformal field theories, which have a very large symmetry group, the superalgebras. So these are the superalgebras of superconformal field theories, and then we can try to use the symmetries to get some mileage. So these are, this is the complete classification by Nam of the different superalgebras which contain the conformal group plus some R symmetry. They can't exist above 6 dimensions, and then in 6 dimensions there's this whole family labeled by n. In 5 dimensions there's only one, which has 8 supercharges. In 4 dimensions there's n equals 1, 2, 3, and 4, and 0. And then in 3 dimensions, again, there's this whole family labeled by n, and in 2 dimensions we can have separate n left and n right. And one could study the unitary representations of those algebras. And so if we have, in fact, a unitary superconformal field theory, the operators are in unitary representations of those superconformal algebras. And this was studied briefly. This is a PLB, so it was very brief. In this paper, and then Shiraz Minwala's excellent paper in 97 studied all of these cases. And so the picture is that at the bottom of the multiplet, There's a superconformal primary, which is annihilated by S's. So they're the Q's, and then they're the Hermitian conjugate operators in radial quantization, which are the S's. The Q's square to the P's, and the S's square to the K's. And so we start off with the operator at the bottom, and then we make descendants with both Q's and P's. And imposing unitarity says that the norm of all of these different operators has to be non-negative, where the norm is using the radial quantization inner product. And so this gives some unitarity bounds. And these bounds are saturated by short multiplets. So in the short multiplets, some of these norms are 0, and then those operators are called null, and then we set them to 0. And if we're only looking at, so in the end, when we look at these superconformal representations, they form a supermultiplet of conformal representations. And so if we only care about that supermultiplet structure, we can basically look modulo descendants. And so effectively, the Q's anti-commute. And so this is some Grassmann algebra, so we can form descendants like this by anti-symmetrizing in L at level L, where L is something that's less than or equal to the number of supercharges. Okay. So in the work, in collaboration with Clay and Thomas, we classify the structure of these multiplets in all supersymmetric deformations. So a deformation is supersymmetric if, when we act on it with Q, we get 0 up to a total derivative, or in other words, up to a conformal descendant. And the structure of the multiplets looks like this. So they're the generic or long multiplets, which are kind of like a walk in the park compared to the others. So these ones, what happens is that there are no null states to worry about. There's an operator at the very top, which is supersymmetric because we've acted with as many Q's as we possibly can. This is like a D term. So we can add a term like this to the theory, and that's like a D term deformation. And it might be very complicated. In general, it is because of the group theory, because these Q's transform in some representation of the group, and all of these descendants, there's some problem of decomposing the tensor products. But it's basically straightforward. And if all you care about is what's the operator at the top, then it's very straightforward to find the quantum numbers of the operator at the top. Okay, the next most difficult case is the generic short representation, where we have to proceed with a little bit of caution because there are these null multiplets that we have to discard, and it gets to be a little bit of a pain to discard the null multiplets and make sure that we don't get rid of too much when we're getting rid of them and things like that. And so a little bit more caution is needed. This RS stands for Rocca-Speiser, which is some way to try to speed it up a little bit, but caution is needed. And in that case, we can find that the top of the multiplet is something like an F term. And so this is another deformation that we can have. And then there are the non-generic short representations, which it's like a zoo of sporadic different cases. If I were to draw what some of them look like, it looks kind of like the bat plane or something. And so they look complicated. You can find some of these cases in Dolan and Osborne for 4D n equals 2 and 4. And we analyze different algorithms to eliminate only the null states. And many different possible algorithms have many different possible problems. It's non-trivial. We conjecture and test a general algorithm in a work that's to appear. So the unitary constraints worked out by, for example, Shiraz apply to these operators here at the bottom. And then what we do is once we've identified the top operator, we can use those unitary constraints to find the constraints on the top operator. And in general, as we increase the number of dimensions or the number of supercharges, there are fewer or no relevant deformations. Okay, so it is kind of a zoo, and in the zoo there are things like animals with more than one head. So this would be like an animal with more than one head. There's some multiplets, like for instance the 3D n equals 4 stress tensor multiplet, where one of the tops of the multiplets is the stress tensor itself, and then there's another head over here, which is also the top of the multiplet. If we act with another supercharge, we get a null state. And so this gives another deformation of the theory. This was in fact mentioned in Thomas's talk. And okay, as far as we know, these kinds of things with two heads, well, it can happen in other cases. For instance, it also happens in 4D n equals 4, where the exactly marginal operator deformation, the stress tensor, are two heads of the same multiplet. But it especially happens in 3 dimensions. Okay, so we give a complete classification for 3, 4, and 5, and 6 dimensions. And we're not exactly taming the superconformal field theory zoo or freeing the SCFTs. Sorry, this is some old reference which will be lost on many. But we give a detailed tour and full picture of the many different multiplets and a complete classification of all SUSY-preserving deformations. And they can be the start or the end of SUSY RG flows between the UV and the IR fixed points. Okay, so just to give an example of one of the tables from our paper, this is 4 dimensions, n equals 3, where all of the operators are irrelevant. This is the dimension of the operator. This is table 25 out of many other different tables, so people are welcome to go and look at these tables. And they can find the quantum numbers and operator dimensions. Okay, so going to the main topic of this talk, which is 6-dimensional superconformal field theories and quantum field theories, we show that there are no supersymmetric relevant operator deformations of 60 superconformal field theories. The only way that you can deform these theories, in fact, is by going out along the moduli space. And then the theory flows to a new low-energy theory plus some irrelevant operators. And we know what the possible irrelevant operators are from this classification. So this is spontaneous conformal symmetry breaking. The low-energy theory has a massless dilaton with some irrelevant interactions. Again, these irrelevant interactions are in our tables of possible supersymmetric irrelevant interactions. We could apply, we can Seiberg the problem and look at the global symmetries. In this case, the global symmetries have a 6-dimensional analog of 't Hooft anomaly matching conditions. The 't Hooft anomalies can often be exactly computed by inflow or other tricks. And there's also anomaly matching for the broken symmetries. So if a symmetry is spontaneously broken, we should still apply anomaly matching for them. And then what happens is the Nambu-Goldstone bosons can contribute by some kind of interactions in the low-energy theory, like Wess-Zumino-Witten terms. In 6 dimensions, the details are different, but morally it's the same. And we can ask about the 6-dimensional A theorem. It's unclear without supersymmetry, and we proved it for SUSY flows on the Coulomb branch, and the Higgs branch is in progress. Okay, so I'll be discussing more about the anomaly polynomial. So in D dimensions, the anomaly polynomial is a D plus 2 form, and this is only really interesting if D is even. And this form can have these different kinds of terms. One term involves only the gauge fields. So these are the field strengths for the gauge fields. And this has to be 0, otherwise the theory is inconsistent. And for example, in this 60 paper that Nati that I showed, that Nati wrote 20 years ago, these gauge anomalies were used, were canceled. The theory had some reducible gauge anomalies that were canceled with a tensor multiplet. So this has to be consistent for the canceled for the theory to be consistent. Then there are anomalies for global symmetries and the gravity and the background metric. And these are, let's call these 't Hooft anomalies. So these are very useful because they're, as far as we know, they're constant on renormalization group flows. So they have some matching relations, and that makes them useful. And then there's the possibility of mixed anomalies, which, as far as we could tell, haven't been much discussed in the literature, but we'll discuss these too in a little bit. So I'll defer this for the moment, but just to set the stage, if we think about 6-dimensional 2-0 theories, the anomaly polynomial, in that case there are no gauge fields, so everything is just a background field. This is what I would call here these 't Hooft anomalies, and it takes this form. There's a free piece. This is what you would just get if you were along the Coulomb branch by adding the rank of the group tensor multiplets, and then there's a piece that knows about the interactions. And this piece was computed by Harvey, Manassian, and Moore for NM5 branes using inflow to be n cubed minus n. This was the first hint that these theories have n cubed degrees of freedom, which is very important. And then by studying this theory and the Wess-Zumino Witten type anomaly matching conditions, I made some guess which turned out to be right about what this thing should be for the other cases. And the fact that this guess turns out to be right was shown by these authors here. And so this is some exact info about the mysterious superconformal field theories. These same things apply also for the little string version of these theories. The little string version of these theories just differ by some massive degrees of freedom, and so that doesn't affect these anomalies. And it's been a long-standing hunch. It was mentioned in this paper of Harvey, Menasian, and Moore from 1998 that there should be some analog of the supersymmetric multiplet of anomalies as known to exist in lower dimensions, where it should be possible to relate the conformal anomaly A to a Hooft-type anomalies for the superconformal R symmetry in 6D as in 2D and 4D. So the idea is that this stress tensor and the R symmetry are in the same supermultiplet. Or if we think in terms of background fields, the metric and the background for the R symmetry are in the same supermultiplet, and this is like a background supergravity supermultiplet. And then, because we're in 6 dimensions, A is related to the 4-point function. How it's related to the 4-point function, who knows, because there are too many indices and it's too complicated to know how it's possibly related to this 4-point function. But by supersymmetry, it should be related to something that's easy to identify, because the anomaly, we know it's like an epsilon tensor. There's no problem to identify what term is the anomaly. And so it's easier to isolate the anomaly, and it enjoys anomaly matching. So this long-standing hunch would be very powerful if it's true. And now in terms of the theory on the moduli space, what we need to do is to supersymmetrize the dilaton, low energy effective field theory. So we have spontaneous conformal symmetry breaking. There's a dilaton which has just derivative interactions. And among the derivative interactions is something that makes up the delta A anomaly, as was argued by Schwimmer and Tyson along. Well, these arguments were in 4 dimensions, but then the same should apply in 6 dimensions. But the difference between 4 dimensions and 6 dimensions is that in 4 dimensions, delta A was the term was related to this 4 derivative term, which was constrained by unitarity constraints. And in 6 dimensions, it's the 6 derivative term. And there is a 4 derivative term, but its interpretation at this level is kind of mysterious. And so this was studied in the paper by Maxfield and Sethi and by Elvang and collaborators, who showed that B is always positive because of like dispersion relation unitarity arguments. But we can ask, what's it good for? What's its interpretation? But as a clue, they noticed that for the 2-0 theory on the Coulomb branch, in fact, delta A was related to B squared. And in fact, Cordova, Dimitrescu, and Yin proved this relation in general for using 2-0 methods, and our parallel work proved it for 1-0 theories on the Coulomb branch. Okay, so just to say a little bit about 1-0 theories and what their moduli space looks like, it's like the familiar kind of setup for theories with 8 supercharges. There's a Higgs branch and a Coulomb branch, but here the Coulomb branch we call a tensor branch because it's related to a tensor multiplet. And in the simplest case, the tensor multiplet might just be one real scalar. And so then that one real scalar should be, for instance, the dilaton itself, if we've spontaneously broken conformal symmetry. So this tensor scalar is the dilaton. If we go on the Higgs branch, then we have lots of scalars because it's a hypermultiplet, and the dilaton is somehow mixed up among these other, basically the dilaton is then mixed up among the SU2R Goldstone bosons because the SU2R symmetry is spontaneously broken, so it's a little bit harder to identify it. So this tensor branch seems a little bit easier, so this was the first case that we looked at. And okay, now coming to the Hooft anomalies for 1-0 theories, the Hooft anomalies can have this form. So the different backgrounds are a background for the R symmetry, it's an SU2R symmetry, a background for the metric, which is this term, and then some mixed background for them. And this is exactly computable for many 1-0 superconformal field theories by these authors who are maybe all of these authors are maybe in the audience. So for example, for the theory of n small E8 instantons, this was the answer that they found. Just as an aside, this theory is often, I don't know why, but it's often called the E-string theory, which is a very confusing name because the name can be applied to both the quantum field theory and the little string theory version. One of them is a string theory, one of them is a field theory, but okay, this is just an aside. If we look at the theory on the tensor branch, there's, actually, how much time do I have? I realize okay. On the tensor branch, there's anomaly. These Hooft anomalies have to match on the tensor branch. And so if there's an apparent mismatch, it has to be compensated for by something. And the way that it can be compensated for is by something like an analog of a Green-Schwarz mechanism. I guess this is Green-Schwarz, West, Nati. Something like an analog of that, but instead of being for gauge fields, it's for these background fields. So if the apparent anomaly mismatch is, for example, a perfect square, then it could be canceled off with one tensor multiplet. Or if you have some number of tensor multiplets, it could be the sum of that many perfect squares. And so you couple this kind of square root of delta IE8 to the B field, and then you could cancel the mismatch. And there's also a quantization condition because this gives backgrounds for like R-symmetry instantons and metric things like that look like gravitational instantons. Those backgrounds effectively then become charged under the B field. And because the B field has quantized charges, these coefficients which are related to those charges should better be quantized. So these are some integer coefficients. Okay, so if we look at this low energy effective field theory on the Coulomb branch, we know just from the bosonic case that the bosonic part that it has to have this form, and then what we want to do is supersymmetrize this. And so these irrelevant operators are in our list. Well, this one is in our list, this one isn't in our list, and the fact that this one isn't in our list, we use that to argue that it's actually the square of this one, which was what we wanted to get. And so this delta A is, by supersymmetry, it has to be the square of this operator. And this proves the 60A theorem because clearly this is positive because it's the square of something. And moreover, this B is definitely non-zero by these dispersion relation arguments if the theory is interacting. Okay, and this B term here, SUSY completes to terms in this Green-Schwarz cancellation. So B, in fact, if we write this X4 as having these coefficients X and Y, B, in fact, is this linear combination of X and Y. And this came from recycling a 6D supergravity analysis from 1986 by these authors. So, so this is the upshot of all of this, is that the conformal anomaly A at the origin could be written as this linear combination of the Hooft anomalies. So then once we know the Hooft anomalies, we know the exact conformal anomaly. So for example, using this and the results of OST for the Hooft anomalies of the small E8 instanton theory, this is the conformal anomaly A for that theory. Okay, so this is then something that if someone wants to, they could try to calculate this in some other way from string theory, for instance, from N M5 branes at the M9 wall. Okay, when we come to theories that are like the theories that Nati wrote down 20 years ago, and similar analogs of that, there's a new element, which is that, okay, so those theories start from something that looks like a gauge theory. So it's a gauge theory, it's a matter content, and then there's some tensor multiplet which is there to cancel off the anomalies. And so the tensor multiplets, well, we have to cancel off the irreducible gauge anomalies, otherwise the theory is just inconsistent. And then if there's any leftover reducible anomaly, we cancel that with the tensor multiplet by this anomaly cancellation mechanism. And the low energy, well, the theory that we would write down on the Coulomb branch roughly looks like this. So the Coulomb branch modulus couples to the gauge field this way. The B field, which is the superpartner of this one, couples like this. And if we reduce this theory, for instance, down to 4 dimensions, we get the usual kinds of couplings between, we get the usual superpartner relation between like the dilaton and the theta angle. But this isn't a standard kind of Lagrangian deformation of a free theory. for instance, this coefficient here, C, I wrote here square root of C because C is the coefficient of the anomaly in the reducible part of the anomaly polynomial. And so you have to take a square root, which in fact tells you that that reducible part has to have the right sign. But this is some fixed coefficient, and the theory is only consistent if it has that fixed coefficient. And so it's not like you can just think of this as some small deformation of the free theory. In fact, this coefficient is quantized, and the gauge theory without these kinds of couplings flows instead to an infrared free theory, not a conformally invariant theory. Now, when you apply this formula to theories with gauge fields, what you find is that the gauge fields themselves contribute negatively. And so there's this negative contribution for the gauge fields, which we could get just by plugging it in. For instance, this is what you would have for a free 1-0 vector multiplet. You plug in the Hooft anomalies into this formula, you get A as negative. The negative looks weird, but this isn't a unitary conformal field theory. It's either a unitary theory that's not conformal, or we could think about it as a unitary subsector of some, or as a non-unitary subsector of some theory that is conformal. And in fact, this paper then found the same value of A in a non-unitary higher derivative theory. Okay, so there's something to this negative value of A, but we're not really interested in this negative value of A on its own. We're interested in theories that are conformal field theories, but where this is part of a final answer which should be positive. So we claim that unitary superconformal field theories satisfy the A theorem and also have A positive, even if they have vector multiplets, as in Nati's theories and generalizations. And in looking at this, we noticed and we think resolved a small puzzle. And the puzzle comes back to these mixed anomalies, which is that, well, in general, if we looked at these mixed anomalies, we can ask if they're a problem to have a mixed anomaly with a gauge symmetry and a global symmetry. So for example, in 4 dimensions, we can have a mixed anomaly of this form. So F1 and F2 are, let's say, field strengths for 2 different gauge fields, or a background gauge field for some global symmetry. And the 6th form can either be something like this, which is there for U1. This is the first Chern class or the second Chern class. So this is the instanton number for some non-abelian group. And for example, if we look at just ordinary QED, it's non-zero. So in ordinary QED, this F1 is the U1 gauge field. This F2 could be, for instance, the SU and F left global symmetry. And this is non-zero, but it's fine. We don't have to do anything about it or cancel it or anything. Also, for 6 dimensions, there are these kinds of mixed anomalies. For instance, if we look at the SPN gauge theory of Witten of n small SO32 instantons, here I should apologize also to the session chair for not citing his work, because you can just look in John Schwartz's paper and see that there are these mixed anomalies in this case. So in this theory, there are these mixed anomalies, but by the way, that theory is not a conformal field theory in the infrared. It's either an infrared-free non-conformal field theory, or it UV completes to a let's call it L or N string theory. But anyway, the mixed anomaly is non-zero. And so we could try to interpret what the mixed anomaly means. So this is some kind of interpretation of that. Like if you look at some configuration of the background gauge fields that looks like an instanton, effectively it's charged or it's not gauge invariant. So there's some equation like this, for instance, that the divergence of some gauge currents can be related in some way to the field strengths for both. This is the field strength for this same group, and then these are field strengths for the other groups. Okay, but we want to argue that actually there are no mixed anomalies if the theory is superconformal. So, thank you. So if it's a 6-dimensional theory that's superconformal, so here the C is to emphasize conformal, then in fact you can't have it. So in these gauge and tensor theories, as I mentioned, that there's already a tensor multiplet in the problem. And this tensor multiplet is already used to cancel the reducible gauge anomalies. And so one thing that we could do is also use that tensor multiplet to cancel the mixed anomalies. So we can ask, should this be done and why? this was something that we puzzled over. And the excellent paper of these authors, who are all here, states that, in fact, all of these gauge anomalies must be canceled, including the mixed ones. And the cancellation, but this cancellation mechanism is very important, actually, because it changes the values of the Hooft anomalies. Because when you cancel these mixed anomalies, you have to complete some square, and then when you complete some square, that contributes more to the Hooft anomalies. And we actually like that answer a lot because it helps to give positivity. So this problem that I mentioned of not having positive A with this extra piece, it in fact solves that problem. But we didn't see the justification for canceling these anomalies, these mixed anomalies, especially since they do exist in other consistent theories. But well, here I say prove, we argue for it or prove it by our operator multiplet classification. Because in looking at our classification of the allowed multiplets in 6 dimensions, there's no, actually this was something that we looked at in some broader generality. If we look for multiplets with conserved currents and what kinds of conserved currents, including higher spin conserved currents, could be fit into supermultiplets, many of them in fact can't fit into supermultiplets. And so in fact here this is like a two-form conserved current, which if you just had a non-supersymmetric theory, you can write down a representation of the conformal group that contains this kind of conserved current with no problem. But if you look at the supermultiplets, no supermultiplet contains that. So in this mixed anomaly equation, there's a kind of operator which just doesn't exist in superconformal field theories. And so since that operator just doesn't exist in superconformal field theories, there can't be an anomaly equation like that. So this is the argument that there's no mixed anomaly. These mixed anomalies from gauge and matter fields actually they do have to be canceled by tensors, exactly as was done by these authors. And this turns out to be crucial to ensure positivity of A and the 6D-A theorem for these theories. So for example, if we look at SUN gauge theory with 2 N flavors, 1 tensor multiplet, and the anomaly cancellation for the reducible gauge anomaly and the mixed anomaly between gauge fields and R symmetry, and use this formula that relates the Hooft anomalies to A, what you find is that A has different pieces corresponding to these different components. So the gauge fields contribute negatively, so this looks dangerous. The hypermultiplets contribute positively, but much less. I mean, this is minus 251 over 210, and this is plus 11 over 210. And then there's the tensor multiplet, which doesn't even grow like n, so that's going to be useless, for instance, at large n. But then fortunately, this extra piece from canceling these mixed anomalies also grows like n squared, just like these other ones, and it's nice and positive. And it's enough positive to win over this one. And so in the end, A is in fact positive. And it can likewise be checked that other generalizations of these theories have positive A, and we're also looking at showing that the Higgs branch flows in general satisfy the 6D-A theorem. Thank you. So just to conclude, conformal field theory is vast. It's full of interconnections. Supersymmetric quantum field theories and superconformal field theories and renormalization group flows continue to be rich testing grounds for exploring quantum field theory after many, many years. And here's to also many years of Nati's path-leading and inspirational contributions, past and future. Here's also to many years of friendship. It's wonderful also to be here at this workshop and to have kind of a reunion of so many old friends and to celebrate Nati. So happy 60, Nati. 60 is the new 40, as they say, and many more happy years.
So there's a lot of experimental data on these superconformal theories, mostly from F-theory constructions and the like. And I'm sure they have a lot of conjectured consistency conditions. Do you derive all of them from your methods, or did you leave something for others to work on?
Yeah, that's a very interesting question. In fact, Yuji told us some interesting things that we're in fact trying to understand some way to. There are many things, yeah, that just come. Yeah. So the experimentalists have, or maybe like the computation, someone has handed us many interesting things to try to explain just directly from field theory.
Any other
That was
questions?
a nice question, thank you.
Yeah, has your work led you to any insight into the question of non-supersymmetric conformal field theories in higher dimensions?
Oh yeah, that's a great question. Well, no, but it's a great question, and so it seems like something yeah, it's definitely one thing one could do. For instance, is take these superconformal field theories. We analyze the supersymmetric deformations, and we argue that, for instance, in 6 dimensions, there aren't any relevant supersymmetry preserving ones, but there are plenty of relevant supersymmetry breaking ones. In fact, some that always have to be there because they're together with the stress tensor. And so, yeah, then it's a great question to ask where it ends up. And in some cases, it ends up at a theory which has to have some massless degrees of freedom, but we don't know necessarily if it's interacting or free. And many people have thought about these kinds of things, but there hasn't been a concrete paper that, as far as I know, that really pushes it as far as it could be pushed.
Any other questions? Okay, let's thank Ken again.